Good morning, everyone. Welcome to Hawkridge Systems webinar Wednesday for June 29th, 2016. My name is Damon Tordini. I'm the product manager for SOLIDWORKS Plastics in SOLIDWORKS Flow Simulation here at Hawkridge Systems. We're going to be doing a presentation today focused mostly on SOLIDWORKS Plastics and specifically how you can use that tool to optimize cycle time during the injection molding process. Basically speed up the throughput of your production. Let's jump in and we're going to talk about optimizing cycle time, SOLIDWORKS Plastics. So, if we're talking about mass production, of which injection molding is an example of, how fast do we need to go? Of course, you probably are aware that anytime you want to gear up to produce some parts via injection molding, some of the costs are more or less going to be fixed. You know, the mold, of course, is going to cost a certain amount, although that's going to vary depending on the design of the mold. But other costs may not be fixed. For example, you know, we all know that you're going to need electricity and maybe water and labor to run the molds if you're associated with the actual manufacturer itself, or maybe you own the molding machines. But what if you could produce the same number of parts in less time? That would theoretically save money, right? As an example, this is on the right-hand side of the screen there, a picture of a retired Lego mold. And that mold produced 120 million Lego bricks over its life. Looks like it's an 8-cavity mold there. So a simple question, if back in the day whenever that mold had been designed and manufactured, if a couple changes had been tried out that maybe could have shaved 1 second, 2 seconds off the cycle time, maybe from either just reducing the fill time required or the hold pack time or maybe the cooling time, how many more of those Lego bricks could we have made with the same mold? Well, that's a question to ask, and of course, you know, we can't really know the answer to that unless we would, you know, truly manufacture those different molds and compare them, and that's obviously not something you'd ever want to do. Ideally, you're only going to make one mold and hope it works. So potentially what we could do is use some software to predict what the impact of these kinds of changes will be. We all know, of course, that the main point of using software like SOLIDWORKS Plastics and other tools is to try to prevent you from having to do mold rework. Just like when you're designing other products, you try to reduce the amount of physical prototyping you might have to do. But in addition to preventing mold rework from needing to be done, the SOLIDWORKS Plastics can also reduce costs and save time and money in another way, which is to make sure that the mold and part that you're designing is already optimized to cost the least amount of money while you're making it. So this is a potential kind of return on an investment in two ways. We're going to assume here that we already are taking advantage of the prediction of what our mold will do so that we don't have to redesign it or rework it after it's made. But we're also going to make sure that the first mold that we build is the fastest mold too. So of course, tools that can do that are part of our simulation offerings, which is one of the kind of many categories here at Hawkridge Systems in which we have tools and services available. And the product specifically is called SOLIDWORKS Plastics. It's part of the SOLIDWORKS simulation family, just like the stress analysis tools we have and SOLIDWORKS Flow Simulation. In fact, there's some interoperability between these tools, as we'll talk about a little bit later. You can even do things like, for example, see what more realistic stress results would look like by taking advantage of simulations you've run in plastics to get a better idea of the material properties. You know, what are the real material properties? So again, what is SOLIDWORKS Plastics? Well, basically, it's a tool to simulate the entire injection molding process. We're talking about filling the cavities in the mold, holding them, holding pressure, and waiting until they've cooled and they're ready to be popped out. The parts are. So we have a large database of plastic materials in that tool to help you get a realistic result, and a comprehensive range of different types of predictive tools that tell you all sorts of things from cycle time, like we're talking about here, to whether the part will fill, if there are any potential defects or quality issues, how much shrinkage and warpage there will be, and a lot of other things. And of course, because it's inside SOLIDWORKS, it's a very easy to use and practical tool for any design engineer. And you're going to be able to evaluate these things throughout the design process while you're still inside SOLIDWORKS without having to go to another person or another program or another procedure. So let's take a look at a little case study here. I've got this Tupperware container that I've been tasked with making. So it's a very simple little box to put my sandwich in. I've got, of course, the main container and then a lid that's going to be hinged onto the top of it. So if I want to make sure that the mold that I'm building is going to make these parts as fast as possible without reducing the quality, but make them as fast as possible so I can save a bit of money on the productions, there are some different aspects I need to think about. First of all, what about the part design itself, right? I probably designed this thing to be the right size to hold, as big of a sandwich as I want and to not crack if I drop it on the ground and other things. But is the part design also optimized to have a good cycle time, not just to make sure it can fill, but to fill quickly and not have other issues? What about when I actually design the mold to make these things? I probably want to make them at the same time since they're both the same material and I want them to have similar properties. So what's the right runner layout for those things? And then also, what kind of cooling line or other aspects of the mold design will I need to make sure that I can actually keep everything at the right temperatures that I want? Can I actually make this thing with sort of the assumptions that I'm starting with? Well, SOLIDWORKS Plastics can help answer all of those questions. So let's look at the kind of breakdown. SOLIDWORKS Plastics has 3 packages which have different capabilities. And basically, each of these is kind of geared towards maybe a different party in the injection molding process. Plastic Standard is largely geared towards the part designers who maybe are just concerned about those first questions. Again, is the part design itself optimized to fill quickly without any, let's say, weld line or sink mark issues? And of course, is it optimized for a quick filling and cooling time? Plastics Professional adds some capabilities that any mold designer would want to help you evaluate a multi-cavity mold, again, which is something that we're going to need to do here. Things like figuring out what the runner should look like, and then what the full cycle time would be. Not just fill, but pack and cooling as well. And then Plastics Premium, the third package there, is for anyone who wants to get more detail and do a true realistic simulation of what the mold will really do. And that entails not just predicting what the warped shape of a part will be when it comes out of the mold, which sometimes is the biggest defect, but it also includes cooling analysis to figure out not just what the part would look like under ideal conditions, but what are the temperatures in the mold in reality based on the material that I pick for the mold and the size of the mold and the cooling lines in the mold and those other aspects. And of course, all of those things can have a huge impact on what your result really looks like. So let's look at the first aspect of this, the part design side. Can a simple change in the part design improve cycle time via cooling or fill time or other things? Well, let's take a look. So first of all, if you open SOLIDWORKS, of course, you can run SOLIDWORKS Plastics to simulate this injection molding process on any part file. So let me first open the assembly that I've got for my Tupperware container, and then I'm going to open up one of these parts to simulate the injection molding process on that part by itself. Of course, you would never manufacture something in this kind of assembled state with the hinge there, because you would have a solid hinge that doesn't move. So instead, of course, we're going to simulate the injection molding of these things separately. So I'll open up the part file, and I can start to do that by turning on the SOLIDWORKS Plastics add-in. You can see I've got it enabled right here, my SOLIDWORKS add-ins tab. And basically what I can do is go through a wizard-like interface to start setting up and running just a simple fill check. Right? I'm not really concerned with any detailed mold design or runner layout yet. I just want to know from the part itself, first off, is it going to fill? And roughly how long will it take to fill? And then are there design changes I could make to improve that or other aspects of cycle time? So I can go to my Getting Started wizard here. Gives me a little introduction, reminding me what this tool is for, of course. And I can go through these steps to get this first pass check. And so the first thing I'm going to do is generate what we call a mesh, which is going to break this part up into individual pieces that the software can then analyze and, of course, simulate the flow front, the plastic itself, flowing through the cavity and then eventually solidifying. Just a little side note here, we have two kinds of mesh in SOLIDWORKS Plastics. There's shell and solid mesh. In this particular case, just to make things a little faster and more streamlined, I'm going to use the shell mesh because this is a thin walled part. However, just a side note, if you really were interested specifically in cooling analysis and how long something is going to take to cool and how much shrinkage there would be, which is also a factor in the pack and hold cycle, in many cases, it would be advisable to use solid mesh, especially if you've got thicker internal regions of the mold that may be the big problem with cooling time. But for now, let's use the shell mesh. Let's go back here and we'll generate that again. So essentially on the left-hand side, the meshing wizard will pop up. And what we can do, of course, is first off confirm that my part here that I've modeled is representing the empty cavity of the mold. So I don't actually need to model the mold and hollow out a cavity or anything like that. Plastics knows that this part represents that shape. And then what I need to do is pick a size, for example, let's say 1/2 inch, and then I can hit this mesh button to see what my initial mesh looks like. You can see here that it's decently detailed in a lot of areas, but maybe some features don't have enough detail yet, like for example these holes. So one thing we can also do is, of course, change the size of the mesh to add a little more detail. That's going to make the calculations take longer, but we can do a sort of a hybrid approach here where we can select automatic under the local refinement, and that's going to get us, or at least try to get us, the best of both worlds, where it's going to go and refine the mesh in those small detailed areas where we need it to, like the holes, without refining it everywhere else. So we can get much better results without as much of an increase in the solve time. And of course, you can manually control the mesh too if you want. In fact, the meshing controls are really comprehensive. You can even do things like add or delete individual elements. But most of the time, we like to leave that to the automatic mesher here, as long as the result looks good, which it does. So now that we have our mesh, we can pick our material. And again, one of the nice things about SOLIDWORKS Plastics is the comprehensive library of polymers that it has. We have approximately 4,700 polymers in our library, and actually some of them are thermoset materials rather than plastics, so things like rubbers and epoxies if you're into that. And in this particular case, this Tupperware container is going to be made out of a nylon material, so we can go down and find, there's polyamide 6, and you can see that we've got real plastics from real-world manufacturers with the actual grade number of the material. So here is BASF Capron 8200 nylon. We've got all the properties in here, of course. This is what we call the rheology data that knows how the plastic will flow around and solidify based on temperature and viscosity and things. But we can simply click OK, and we're ready to go. You also notice that the library knows what the recommended temperatures are. So how hot we want the melt to be when we inject it, and what temperature we want the mold to be at. Okay, now we can also set what we call the fill settings, which is basically how quickly we want to try to fill the part. And so I'm going to put in about 2.5 seconds here. You can see there was an automatic value, and that's based on the volume of the part, but we can override that and basically try to fill the part a little more quickly, which is what we're talking about here. And Plastics is going to calculate how much pressure we need to do that. And of course, if the pressure gets too high, in fact, if it gets above this injection pressure limit, which is going to be based on your actual molding machine, then the software will tell you that you have a short shot. And so that's, of course, how you know whether or not your part can actually be made or whether you'll have a failure to fill. Finally, we need to pick an injection location. And if we're talking about just a single part here, that's the gate location. SOLIDWORKS Plastics, of course, can do things like predict the best gate location for you. You can use the automatically add gate locations option, or you can add it yourself. I'm going to put mine more or less in the middle of the part right here. And I'm going to type in the size of the gate. And I can even get a nice preview of the fill pattern. And as I would expect, the top edges here are going to be what fills the last. So now that I've got all this setup done, I can run my analysis and I can get a first prediction of if the part will fill, but more importantly, I'll be able to start looking at the things that would affect the overall cycle time. So here we go. This particular study is going to run here real time on my computer, and it's about 14,000 elements, as you may have seen over there. And just to give you a comparison, on a typical kind of desktop or even laptop computer that meets the regular requirements for SOLIDWORKS, you should be able to run a study like this with at least several 100,000 elements, unless you don't have that much RAM. I, for example, have 8 gigs of RAM on this computer. So this is going to take about 60 seconds or so to complete. And at the end, we'll know how quickly we were actually able to fill this part. We were shooting for 2.5 seconds. And then we'll be able to explore some things like, does changing the part design improve the fill time, or might it even improve the cooling time too? So here we are, we're at about 80% filled now, and we can see actually some partial results in the analysis manager there on the screen. We're currently at about 21 megapascals, which is also about 3,000 psi of pressure. And that's fairly low. The default molding machine that we have in the software assumes 100 megapascals of pressure. So we're only about 1/5 of the total of the maximum output. And by the way, that default it's kind of an analogy for a very low-end molding machine. In the real world, it's very likely that manufacturers are using a more powerful machine for any of these multi-cavity molds especially. So when the analysis is complete, we get this results advisor, which is going to pop up on the right-hand side of the screen. And very quickly that tells us, first of all, that the part can be filled. It ended up needing about 30 megapascals. And more importantly, it looks like we were able to fill it in the desired time of about 2.5 seconds. So at the moment, we don't need any design changes, for example, wall thicknesses, just to get it to fill in the amount of time that we were hoping for. So that's good. But we can start to look at some other aspects here. For example, quality issues like weld lines, or maybe air traps if we were concerned about that. But also temperature and pressure results. And that's going to give us a prediction of how long the other stages of the injection molding cycle will take. We can see here, for example, that the central temperature, which is basically the temperature right in the middle of the cavity, at the end of the fill, it's still going to be pretty high. We've got about 500 degrees in a lot of these areas, particularly here. And we can even get a very kind of rough estimate of what the cooling time might be, just based on those temperatures and also some geometry. So for example, these areas above the hinge here look like they might be problematic, just because combined with that little lip which the lid is going to sit on, doesn't look like there's enough surface area to get the heat out. So of course, one thing we could try is a design change to see if any of these aspects are improved. So what I could do here is, of course, make another configuration in SOLIDWORKS. Some of you may use configurations just to create different sizes of the same part or different revisions. That's what we're going to do here. We're going to create a new revision with a change in it so that we can compare to the first one. So I've created a configuration called RevB. And basically what I've done is just made a little cut. You can see here that I've got a cut extrude based on this sketch that I made. And that's basically going to split my hinge in half right there, just to cut a little slot out of it. And with that added surface area, we can see if perhaps the temperatures drop, which of course should reduce the cooling time. Now, aside from this check of fill and cooling time, a change like that might have some other implications, like for example, is the hinge going to be strong enough still now that we've done that? Well, that's the benefit of having all of these tools integrated into SOLIDWORKS. if I made that change, I could go back to any stress analysis that I had already done as part of the SOLIDWORKS simulation tools. Maybe just a simple static analysis of, let's say, a force on those hinges. And I could make sure that even if I cut that slot out of material, that they don't bend too much. And I don't have to export my model or go to another program or prepare it for some other kind of analysis. I can do it right inside the same interface right when I make this change. And so once I verified that the stress side of things is going to be fine with this change, now I can go back and I can see if it makes a difference in the injection molding. So we would simply go here back to plastics, and so to make sure that we don't have to start from scratch, what we could do here is go to the model manager inside SOLIDWORKS Plastics, and we can see a list of some different plastic studies that I've already created. Here's the default one, and I could simply right-click and copy that, and then paste it, and give it the name of my new configuration, and that would preserve a lot of the setup for me, so that I don't have to go back to start over again. So you can see here, here's the new mesh, which now includes this small cutout that I've put into the hinge. But otherwise, all of the other conditions are the same. We've still got this Capron 8200 material. We've still got the injection location in the same spot. And our other process parameters are the same. Fill time, temperatures, and the pressure limit of the mold. So we would run this analysis, of course, and go get some flow results. And so again, the first thing we'd want to verify is just to make sure that we can still fill the part in the same amount of time, because that's the thing that's most important at this stage of the process, just making sure we can fill it as quickly as we hope. And it looks like we can. In fact, we again have this results advisor, and surprisingly, that change actually reduced the pressure just slightly. So our molding machine had a slightly easier time filling the part now. And if we look at some of these other results, like for example, central temperature, we can see that now the temperature in the hinge is a little bit lower than it was relative to the rest of the surrounding geometry. And we can even look at that cooling time plot, and we can see that although the cooling time now is a little more uniform in the whole hinge, it has gone down a bit. So it should reduce the overall cycle time in that sense. And in general, it just seems to be a better design in all aspects, quality and otherwise. So that's the initial stage of optimizing your part design for manufacturability before you even worry about what the mold looks like. And that's really what the SOLIDWORKS Plastics standard license is intended for. Okay. So once we've checked those fill-related aspects, let's go on now and let's try to get into more detail about what the mold itself should look like and what the cycle time itself will actually be, both for packing and cooling. We all know probably that when you're making a part, the fill is not really the biggest component of the overall cycle time. Pack is typically just as long as fill, maybe longer, and cooling probably is the biggest time hog. So the question is now, when we want to go build the actual mold to make these two parts, not just the base, but the lid as well, what's the right layout for that mold? And what are the right sizes for the runners to make sure that we still have a good fill time, among other things? So now we can use some of the capabilities in Plastics Professional to answer those questions. So I'm going to switch to another configuration I've got here. And so this is still inside the part file for the bottom of my Tupperware container. But what I've done is I've added in the other part, the top lid, using the insert part feature. So even though this is not an assembly, I can have multiple bodies. And then what I've also done here is created a little sketch, and that sketch can represent the runner layout for me. So of course this is just kind of a baseline design, may not be perfect yet. I might decide that I want to make more than just one full product per mold. I could have a 4-cavity mold or other things. But for right now, let's just try to go with this first baseline. And so what that will entail, other than the other steps that we've already covered to this point, is specifying the runners. Everything else would be the same as far as meshing and, of course, picking our material and the other aspects of that. But for the runner system now, what we'll need to do is go into the channel design set up under the plastics project tree. And what we can do here is specify what the runner looks like for each of these segments of the system. We can select things like the shape of the runner, whether it's circular or square or trapezoidal or other things. And then we can choose what the sizes of the runner should be. We can see here this is actually the sprue of the mold, and what I've got here is about a 5/8 inch sprue at the top, going down to a 1/2 inch at the bottom here. Then I've got 2 1/2 inch runners going off to the side, and then finally I've got 2 gates here which end up at about 1/4 inch where they contact the part. Now when you do a full mold layout like this, what we're going to change about the injection location is to specify that at the top of the sprue, because we've already drawn in where the gates are going to be. So you can see here now I've selected the top up there. It's just the end point of my sketch line. And so that's where the plastic will flow from, of course, through the runner system and then down into the cavities of the mold. Now this is not going to be this is going to be a cold runner at the moment, but if I wanted to, I could specify a hot runner system, which will assume that I've got heating elements in the mold near the runners to prevent them from solidifying. And that's another way that you can potentially increase cycle time and potentially increase assembly time too, or actually speed it up, I mean. So we can run this analysis here, and even if we just want to run the flow results at this point, if we're not yet worried about the full cycle time, we just want to know if this is still filling properly, we can do that. We don't have to run the pack or warp yet. So let's go to our flow results, and we shall animate this. So it looks like now my full mold layout is filling, but there's a difference. It says my cycle time is now more like 3 seconds, a little above 3. So why is that? Why did my cycle time take an extra 1/2 second than I expected to? Well, we can go look at a pressure plot here, and this gives us part of the answer. You can see that we've actually maxed out the pressure of our molding machine. We have gone up all the way to the full 100 megapascals, which is what the advisor is telling us here. And so because of that, our flow rate is going to be dropped, right? We are not able to fill as fast when we max out the pressure. And part of the reason for that, if we continue to animate this, is that you can see the mold is filling unevenly. As you would expect, of course, one part is a lot bigger than the other. The bottom is a lot bigger than the lid, so it's taking longer to fill. So to reduce that cycle time, of course, one of the challenges of mold design is sizing the runners properly so that the cavities do fill at the same time and at the same rate. And that'll, of course, kind of use the output of the molding machine more efficiently and hopefully fill up the mold in less time. So how do we do that? Well, we could, of course, go and change those runner sizes ourselves. We could just type in a different size and run the analysis again. But that could take a long time to figure out exactly what works. Thankfully, in this license of SOLIDWORKS Plastics Professional, the middle package here, we have the ability to do what's called runner balancing. And this runner balancing tool allows me to go in and specify a range of runner sizes, a minimum and a maximum, both for the runner and for the gates. And this is going to go through and continuously loop the fill analysis of my full mold in the background to figure out what sizes would have the lowest cycle time and basically fill the most evenly. So we would plug in some limits here. Let's say, for example, 0.25 at the minimum, maybe all the way up to 1 inch at maximum, and maybe something similar for the gates. And then, of course, this would take some time to run, most likely somewhere around 10 to 20 times as long as the original analysis, as it continually loops through in the background. But once it's done, we could go here to the finished result, and we can see what we get. It's going to spit out, of course, a new runner design for us as far as the diameters. And we can actually see what that thickness distribution is on the screen. So in this case, when I did the runner balancing before, what we ended up with was a slightly thinner runner leading to the lid. You can We can drop that down here to about 0.475 inches, and a slightly bigger runner leading to the bottom, the base. Same thing for the gates. The gate was enlarged slightly going into the base, stayed about the same going into the lid. And the result of that, if we go look at our fill results yet another time, is that the mold fills now, and it fills more evenly, and it fills in less time. Our cycle time, if you look on the left there, is now 2.48 seconds. So we've shaved a half second off the cycle time of every one of these Tupperware containers just by adjusting the diameter of a runner a little bit without making any other changes. And we've still got tons of other things to explore, like, for example, the actual length or width of the runner, and maybe even the material that we're using. We never even considered other materials. So we're just starting to look into the arena of possibilities here for reducing all aspects of this cycle time. Now, at this point, all we know is that we're still able to fill the full mold in 2.5 seconds, which was my original goal. Now we need to know, how long are the other aspects going to take? How long do we need to hold pressure, and how long does it need to cool inside the mold? Well, the next step, of course, is to run what we call pack phase of the analysis, and that's going to tell you what happens when you continue to hold pressure on the mold and wait for the plastic inside the cavities to start to shrink a little bit. Of course, the purpose of holding that pressure is to minimize the amount of shrinkage, so that as the plastic cools, a little bit more molten material seeps into the cavity, and overall the dimensions end up closer to the cavity dimensions. Now, to run the pack side of the analysis, we just have to fill in a couple more settings. We need to put in what the pressure holding time is and what the cooling time is. Now, the pressure holding time, again, that's the main factor that's going to determine shrinkage. If we put in a longer hold time, or if we, for example, change the pressure profile setting of what pressures we want to hold at, that's going to determine how much the part shrinks. If we determine that we don't need a certain amount of shrinkage, or a certain amount is acceptable, then maybe we could reduce that pressure holding time. Maybe we could back it off from 9 seconds to 7 seconds or something like that. And then for the cooling time, of course, we'll want to try to minimize that as much as possible. And here's a little tip: when you're running these pack analyses, you want to put in a longer cooling time than you need, just because you want to be able to see for sure how long it actually takes for the part to cool all the way. The worst thing is running an analysis where you only put in 10 seconds of cooling time, and it turns out your part isn't cool all the way yet, and you have to go start over to find out how long it would really take. So we can now go run our pack analysis, and when we do that, we could go look at the pack results. So first off, what we need to do is try to find out if the pack time that we put in is long enough or too long or whatever. So the way to do that is we can look at our volumetric shrinkage plot here, and this shows, just as a percentage of volume, how much shrinkage there would have been in the parts. And if you look at that result under the flow tab here, if you see on the right hand side of the results pane, this is showing how much shrinkage there would be without doing a pack. And you can see that in those parts, some of the red areas are showing about 15% shrinkage, and that's way too much, obviously. So that's why we always do at least some kind of a pack for at least a few seconds to try to reduce that amount. Now, if we go over to the pack tab, we can look at this volumetric shrinkage plot, and you can see here that now this is the shrinkage at the end of the packing cycle that we did. And as it turns out, we've got much lower values of shrinkage in here. In fact, we could use the measure tool to see how much there is. The lid seems to have somewhere around 2 to 2.5% shrinkage, whereas most areas of the base are somewhere around 3%. And that's probably acceptable. So we know now that 9 seconds of packing is sufficient. In fact, if we're okay with a little bit more shrinkage than that, maybe 4% or something, we might be able to reduce that packing time even more. Maybe bring it down a second or two. And again, every second here counts and is going to save money. In addition to figuring out if we've packed long enough, We can also look at these results to figure out what the total cycle time will be once you account for cooling. Now we can use what we call the XY plot down at the bottom here to see what that really looks like. And this XY plot can give you a lot of things like the inlet pressure and some other results. But if we're primarily interested in the cooling time, what we want to pay attention to were those hottest areas of the part, which, as we saw in this case, were the hinges themselves. So we could plot the node temperature here. And as we can see, this is showing us where the temperature of those different areas rises up as the part is filled, and then starts to drop while we pack and then begin cooling the part where we aren't holding pressure. And what we can see is when the temperature of each of these areas crosses both the blue line, which is the glass transition temperature of the material, and the recommended ejection temperature, which comes from the material's vendor. So as it turns out, even though a lot of the areas of our part are cooling pretty rapidly, in fact, it looks like it's only taking maybe 6 to 8 seconds to cool some of those areas, we can see one spot, which in this case is right on the top of our hinge here, spot number 1. That's taking a much longer time. In fact, the total cycle time at the moment appears to be about 32 seconds. So it's taking nearly 25 seconds or so to cool, almost all the full time that we had kind of plugged in as a safety measure. So reducing the cooling time turns out to probably have the biggest impact on cycle time. And there's lots of things we could explore there, maybe further design changes, or maybe we could try to change, for example, where the part is gated and the runner layout, and many other aspects to see if there's anything we can do to get this to cool faster from part design or layout perspective. Now, there's another challenge. That is that the results we're looking at up to this point have all assumed that our mold is at the recommended mold temperature of 190 degrees Fahrenheit. Again, that's coming from the vendor of the material. Now we could try different temperatures in that box to see if we still get a good result for the part at a lower temperature, and then of course we could see how much that reduces the cooling time by. And that's all something that we would want to explore up to this point and be useful. But a more important question is, can we actually keep the mold at that temperature? Remember, that's sort of an idealized situation. So even once we've made sure that the part is designed properly, that the mold has the right layout, the runners are the right size, and we have an initial idea of what our cycle time should be, assuming we're able to do the job, we won't really know what the real cycle time is in reality unless we know what the mold itself is doing and what the temperatures of the mold really are. And this turns out to also be very important for things like warpage. In reality, no mold is going to have a uniform temperature. There are going to be hot spots in the mold and cool spots in the mold. And of course, one big challenge in mold design is adjusting the layout and the material of the mold, and most important of all, the cooling line layout, to try to reduce those hot spots and keep the mold at the right temperature. So this is something that we can now tackle in SOLIDWORKS Plastics Premium, the highest license of this tool. So at this point, we are really incorporating as much realism as possible into this design. And so now what we have is, in addition to my mold layout and the runner system, I've also done 2 more sketches to represent the cooling lines in the core and cavity. So that would require one extra step in the setup here. We could go into the channel design once again, and this time we'd be able to go and select cooling channel, and we would click on these lines and simply type in again what the size of the cooling line should be, and also if it's a normal channel or if it's a baffle or bubbler, which are other sort of offshoots that you often see in a cooling line system, which attempt to cool maybe the inside of a part up in the core of it. So what we've got here are some, these are 5/8" runners that are going through the mold, cooling lines, 5" cooling lines, and we can specify some other interesting things like what is the coolant. You can see here I've got water but there are other options like ethylene glycol. And I can also specify my cool pipe, which is basically the temperature and flow rate of the different coolant that I've plugged in. And of course, I'm just going to go with the defaults here, but you may have seen right there that I've got the cooling lines reversed. So the first one is coming in from the right, the second one is coming in from the left. So that way, both sides of the mold hopefully should be cooled. So now when we do this, we have another thing that we can run, and it turns out that we run the cool part of the calculation before anything else. So that actually tells us what our real mold temperature would be rather than our assumption. Once we do that, we can go back and run the flow and the warp again, or excuse me, the pack again. And of course, you can do them all at once, so you don't have to manually click every time. And what that ends up getting you is a much more realistic picture of what will really happen in your mold. We can see here, of course, that there's a mold temperature plot. And as it turns out, the mold temperature, thanks to some of the choices I made, which include, by the way, an aluminum mold in this case. I wanted to see how cool we could get things with a 1060 alloy mold. As it turns out, we are able, in this situation, to keep the mold at the temperature we wanted. And there are some gradients, of course. There are some hot spots that we see at the top of the bottom part of the Tupperware. That's getting it to about 175 or 165 degrees Fahrenheit. Whereas the bottom is the top is a little bit cooler. So maybe there are some adjustments to the cooling line system that I could make to try to even that out more or to even reduce the temperature more. So this is sort of a validation that we'll be able to actually make the mold do what we had hoped it would do up to this point with our assumptions about mold temperature and inlet temperature. But when we do that, we're able to then get the most realistic version of all of our results to date, including fill time, including part temperature at the different stages, such as fill, and of course all of the other quality-related plots like temperature growth or shear stress in the parts will all be improved, as now we have the real mold temperatures rather than an assumption. So again, any defect, particularly warpage, if you're trying to look for the most realistic result possible, can take advantage of the cooling line analysis that's part of Plastics Premium. So what happens at the end of the day? Well, as it turns out in this case, even if we have a really optimized mold design like we've got here, with the right runner sizes and a good mold material and good cooling line design, we can go look at our XY plot here, and as it turns out, our true cycle time for those hot areas near the hinge ends up being about 33 seconds or so. So just slightly longer than what we had originally predicted with an ideal mold temperature. So thankfully we've validated that we will be able to design a mold that fills the parts quickly, that doesn't have too long of a pack time and doesn't prevent shrinkage to an unnecessary level, and that we've got a cooling time that's acceptable and also something that we can actually do in the real world with the right mold material and cooling layout and coolant. And of course, from here, we could explore many other potential solutions to this. Again, maybe improving the cooling line design further, maybe adding in some bubblers, maybe even going back and reevaluating our part design to see if there are other things we could do to knock a few more seconds off. Because remember, if I'm at 33 seconds now and I can knock it down to 30, well, that's about 10%, isn't it? So once again, just to sum up, the various capabilities in plastics, which are normally used to prevent mold rework and, of course, prevent wasted material, can also be used to speed up the process of the manufacture of any part and save time and money in doing so while you're already in the production phase. And those are benefits that, of course, will pay off down the road for years to come. With that, if anybody has any questions, Silvio and I will stick around for a few more moments. We'll try to answer those. Otherwise, if not, thanks again for watching and have a good rest and a happy 4th of July.